Very good morning. Today we discuss 2-way and 3-way analysis of variance. I hope up to last class you got good exposure to analysis of variance on a one-way analysis of variance. Today we discuss 2-way and 3-way analysis of variance. So we start with one-way ANOVA. We continue to 2-way and 3-way ANOVA. And you also see some examples in the process. Let us see what is there for you next.
So far we have discussed ANOVA, which is known as one-way ANOVA. Getting me? One-way ANOVA. Why one-way? Because we have considered only different population in terms of one factor. For example, I say that different processes. We say that process A, process B, process C, like this, and we treated them as if this is population 1, this is population 2, population 3. Now, what is the guarantee that the process will perform equally over the seasons? It may so happen that during rainy season the performance will be bad, then summer and winter. This is one. Second thing is that second issue may be, suppose the process operators, process A, process B, process C, A, B, C is there, but there will be different operator level 1, operator level 2 and operator level suppose your K. Mean who is actually operating the process, that also determine the quality of the process. So, in that case, in the first case or second case, what you require to do, you require to include the effect of operators, maybe the effect of seasons. Now, you do not have control on over seasons. So, even though you know, but you may be some action plan you may be taking, but on the over the that seasons you have no control. So, in that sense what will happen sometimes, suppose we can say that season is a noise variable, getting me, but you want to estimate the process effects keeping in view that the seasonal effects to be blocked. Getting me what I am trying to say? So, that means you will, one thing is that you go for rainy season productions and see the quality, summer production see the quality, winter production see the quality. That means you do not want the noise variable effect to be accumulated in the process effects. If you do like this, this type of design is known as blocking. So, this is one variable is block variable is there. So, rainy seasonal different, summer is different, winter is different. It may so happen that you have control over the operators. So, depending on the situation, you may change the operator, you give the operator to different machines where he may be fit. So, in that case if you have control over the operator, so this process is one factor which is controlling the quality of the product produced, and as well as operator is another factor, that is factor 2. Even here also we can say noise variable, this is factor 2 and process is factor 1. Only difference between the first and second, this blocking and this is, in this case you are not interested to know, or you are not in a position to know this one better is you are not interested to know the seasonal effect because you do not have control on seasons. So, nullifying the seasonal effect or eliminating the seasonal effect, you want to estimate the process effect. Here you want to estimate both seasonal effect, operator's effect plus process effect. This type of design is, this is 2-OA ANOVA. This is 2-OA ANOVA. What will happen here? Why 2-OA? Because factor 1 having suppose A levels, that means factor 1 is having 1, 2 like up to A levels, factor 2 is having B levels, that means 1, 2 like B levels. Then your design is like this. What is your design? In this side you are writing factor A, this side or factor 1, this side factor 2, factor A or factor 1 and factor 2. So, factor 2 is having B levels, factor A is having A levels or factor 1 is having A levels. Okay. Usually we denote as factor A or factor 1, factor B, A B is coming like this. Now, what will happen? You will collect data. Okay. So, factor 1 at level 1, factor 2 at level 2, you collect a large number of data, correct. Here also you collect some data, collect. So, everywhere you are collecting data. If I go by the population concept that what we have discussed in ANOVA, then what you are getting here? You are getting two important things. One is for factor 1 you will be getting here x, if I say this is L bar, I am giving one dot here. What is this? You can ignore factor 2. If you ignore factor 2, then the sum total of observations here, this cell, this cell, this cell, this cell, this observation is related to 1. So, you will be getting 1 average. You are ignoring factor 2. Similarly, here you are getting 2 average, like this here you will be getting A average. Now, you ignore A, you talk about factor 2 only, then here also you will be getting average. So, this one we are denoting like this x dot m, x bar L dot, L stands for all the rows here, that is labels for factor 1, x bar dot m, m stands for labels in factor 2. So, then this will be x bar dot 1, x bar dot 2. So, like this, I think this one x bar dot b, correct. Then here will be one grand average, yes or no? Grand average means I do not consider A or B anything or factor A 1 or factor 2, I will consider total, these are all my observations. So, it will be basically average of all the values given here. Now, as you have computed this XL bar here ignoring this factor 2, so can you not find out that tau L dot this minus grand? Similarly, here also you can find out, yes or no? I think we will not use this one dot, we will not use here, tau L, and similarly here we will use tau M. Then this one will be your x dot 1 bar minus x bar, x dot 2 bar minus x bar, like this, x dot b bar minus x bar. This is known as two-way ANOVA. Getting me? Two-way. One factor 1 A labels, factor B, factor 2 B labels, and there is another issue is known as interaction between the factors. Now, what will be your ANOVA table in this case? In this case, your ANOVA table will be like this: sources of variation. One is factor 1, factor 2 is also source, interaction 1 and 2 between factor 1 and factor 2, and error, then total. You have to find out sum square. So, it is, I can write here sum square A I am writing for the first factor, second one I am writing sum square B. I think we should change little different, because B already for between we have taken for B. So, factor 1, factor 2, factor 2. So, if I write like this SS1 and SS2, no problem, then factor 2, then SS12, then it is SSE, and this will be SST. ANOVA case, it is always basically partitioning the observations into different components, similarly partitioning the total variability into the sources variability. Okay. So, here what will be the degrees of freedom? How many labels are there for factor 1? A level. So, A minus 1. How many labels are there for factor 2? B minus 1. What will be the interaction? A minus 1, B minus 1. What is the total number of observation? A B n minus 1, because see, if we consider that you are collecting n observation here, n observation here, everywhere n observation, there are A levels for factor 1, B levels for factor 2, there are A, B cells, and in each cells there are n observations. So, A, B, n. So, that is what is our capital N. Capital N is A, B, n. Now, if you collect different samples for different cells, as well as if you collect different samples for the factor 1 and factor 2 differently, ultimately this computation will be little different, but the you can still write n, you have to compute n. Okay. Then what will be the SSE's case? A B n minus A minus 1 minus B minus 1 minus A minus 1 into B minus 1, because total will be this. So, what will be this value? A B n minus 1 minus A minus 1 minus B minus 1 minus A minus 1 B minus 1. Okay. So, this is A B n minus 1 minus A plus 1 minus B plus 1. So, minus this is A B okay, minus A minus B plus 1, correct. So, I am writing A B n minus 1 minus A plus 1 minus B plus 1 minus A B plus B minus 1. So, plus A plus minus A plus B minus B minus 1 plus 1, then it is basically this is 1 minus 1, na? This is plus 1, this also cancelled out. So, that means A B n minus 1. So, your okay. Then what you require to know? You require to compute MS, mean square, that variability. This will be MS1 will be SS1 by A minus 1, MS2 will be SS2 by B minus 1, then MS12, that is interaction, which is SS12 by A minus 1 into B minus 1, then your MSE will be SSE by AB into n minus 1. Then you find out F. What will be your F? F basically the concept of F here is here, why we will use in this fashion F. What we want to see, that whether factor 1 variability explanation is more than the error or not, whether factor 2 is explaining equally to error or it is better, or interaction to error. So, that means every sum squares, here we will take the mean squares, will be compared with error. So, as a result, for this F1, if I say for the factor 1, this one will be MS1 by MSE. For factor 2, it will be MS2 by MSE. For 1 2, MS12 by MSE. These are the things you want to test. Okay. Now, what will be the degrees of freedom for this case? If this one greater than, what is our numerator degrees of freedom? A minus 1, and denominator degrees of freedom is AB into n minus 1. If this alpha, this is the case. So, if computed F is greater than the tabulated F, then what will be your decision? Reject H0. So, similarly, if this one is F B minus 1 A B n minus 1, do it. If this one F A minus 1 B minus 1, I think into A minus 1 into B minus 1 and A B n minus 1, then do this. This is what is known as two-way ANOVA. Now, you can go for multi-way ANOVA also. What will happen ultimately? Suppose you three-way ANOVA. What you will do? How do you partition it? Three-way ANOVA case. Three-way ANOVA. That means, if I say factor, I am now writing in terms of ABC, factor A with A labels, factor B with B labels, factor C with C labels. So, if I collect equal sample size, suppose sample size is n. So, your total observation will be A, B, C, N, total observation that will be okay. Now, I will not compute anything, only thing I want to write here, what will be the sources of variation, sources of variation. Definitely first is A, second is B, third is C, then definitely AB, interaction between A and B, interaction between A and C, interaction between B and C, interaction ABC. Correct? See, first is A, second is B, third is C. A B may interact, AC may interact, BC may interact and all three may interact plus error. So, your total variability will be decomposed into different sources. Now, A, B, C, these are all known as main effects. A, B, A, C, B, C, in this case this is 2 OA interaction effects. A, B, C is 3 OA interaction effect. And error. So, you have to find out SS, for everywhere you have to find out SS, then you have to find out DOF, degree of freedom. Degree of freedom is for main effect A minus 1, B minus 1, C minus 1, interaction effect A minus 1 into B minus 1, for AB, for AC A minus 1 into C minus 1, the like this ABC case A minus 1, B minus 1, you know that multiplication, and your for your total case that will be ABC n minus 1, then the for error part just subtract. Once you get all those things, suppose SSA, SSB, SSC, SSAB, SSBC, SSAC, SSE, then SST with all degrees of freedom, you have to compute FA, FB like this, and you know that what will be the degrees of freedom for the tabulated value, that F value you calculate. This is what is the decomposition, and by this manner you will be able to find out the effect of many factors, their interactions. It may so happen that your case is such that there is no effect for B or C, but A, AB, BC, these effects are there. So, that interaction effects you have to control. Getting me? Any question you want to ask me? No question? I think now you are in a position to explain ANOVA for any number of factors.
So, for 3 it is 8, for n it will be 2 to the power n.
Just compute little bit. For 3 this is 2 to the power k. Suppose I have
NC0 plus NC1 plus
in that sense calculate, because it all depends, because 3 factors and how many main effects? 3 main effects. How many interaction effects? So, that means NC1 is coming, then 2 at a time NC2 is coming. So, okay, that way you will calculate. Because 3 factors 2 at a time, 3 factors 3 at a time, 3 at a time will be 1, 1 at a time will be 3, and 2 at a time will be another 3. So, that sense it is coming. So, you calculate, this is okay. Bolo? You ask me some question? It's okay na? So, this is basically the totality from ANOVA point of view. I think ANOVA is very useful, very powerful technique also, and you find out in many cases ANOVA is required, but this is a univariate model, keep in mind. In the multivariate counterpart is MANOVA. So, we will discuss in next class. MANOVA will be discussed in next class. And for ANOVA, I suggest you to follow D.C. Montgomery, Design and Analysis of Experiments. This is the best book I have read in terms of your ANOVA. Large number of real life examples are given. And if you know ANOVA, MANOVA will be extension to the multivariate domain. Little bit computational difficulty will always be there because you will be computing in the matrix domain. This all sum square will become, that also you have seen the matrix domain. Sum square will not be there, it will be SSCP, sum squares and cross product. Okay, okay, thank you very much.